Marcella.
Okay. I prepared some codes to show you the things that I presented on Monday. And I used the given data set for the school. I uploaded the notebook in the repo, so maybe if you have access, you can see here in the HTML file. But I will show you all the code in RStudio. That is actually the environment for R. Okay, so okay. First of all, I developed it in R because I use it every day. But actually, this library that we are going to use is also available for Python. Actually, I tried to prepare in Python, but it was, in my opinion, more complex to teach you. And so it is. I can show you more things with R, but it's completely personal. I think that if you prefer Python, you can use it. So I use this library, iGraph, and this is the program, let's say, to the editor to deal with R programming. Here we have the code, then we have a console to see to print our result, our output. Here we have an environment, we will see in a minute, and here we have the plots. And also some, if you need, for example, here a manual for the package, you have all the information, so it's very useful. So,
sorry, can I ask you make the font size a bit bigger?
I think I can enlarge.
I think it says in tools and global options, you can appearance, and then you can change the font size. Appearance.
To 28.
I think this is much better already.
Okay.
Oh, thanks a lot. This is fine.
Okay. Thank you. Okay, so I can also put a bit. Okay. Because I need also the output. Okay. So I can execute basically line by line here, and I will do it so that I can explain better the code. So we can upload, we can load simply the package, iGraph, and these are color brewer that we will use for the plots. Then okay, this is the path where I put my file, and I upload the graph provided by Stefan. So with this summary comment, we have a first summary of the graph. We can see here that is directed, D, bipartite, with 957 nodes and 1,907 edges. Then we see the list of the attributes, and for each attribute we can see, for example, size is an attribute for the nodes because there is a V that is vertex, and the other letter here, N, tell us the domain in which the attribute takes value. So, for example, this is numeric. Then, for example, we have this active is Boolean attribute for vertex, and then we have, for example, this type is character string attribute for edges. So I can check some properties with some basic function. So I can see, for example, if it is directed, it tells me true, is bipartite true, and we already know. As multiple, yes, so it is a multigraph. Then I will remove these edges that I won't use for this tutorial. So I simply execute all this line. And now, of course, if we repeat, for example, I can also write here. You see, I have a shorter list of attributes. This function remove attributes returns a graph, and actually I can simply use the same variable because it's overwritten. Then I have some basic function to see, for example, here the number of nodes. It prints here 957. Then here we can print all the set of vertices and nodes. You see that to each vertex is assigned to a number that is ed. It is assigned by R. When I uploaded the graph. But I can also have a name. In this case, for example, I have a label attribute, and I can see all the attributes of this node with putting this dollar and then the name of the attributes. So here, for example, I have all the list of all our nodes. Then I can see if I only want to print the different values of attributes without repetition, I use this unique command. And you see, for example, the type of the node can be person or institution. So we have a bipartite network that is an affiliation network, meaning that person is affiliated to an institution in this direction. So the nodes goes from the person to the institution. And if we want to access a specific node, you know, this vertex set is like a vector. So I use it as a vector, and I access with the index, so for example the first, and then I can see the label and the type is Joas Leopold and is a person. And if I want to see all the nodes with a specific attributes for a value, I simply put in the square bracket the conditions. So for example, here we want all the nodes in which type is person, and I can easily obtain, let's say, the subset of the nodes that satisfy this condition. Then I can also assign new attributes to the nodes, and it's quite easy. Here I will assign a Boolean attribute to the nodes, because then I will use to do to manage the network. So I name this BIP, and so basically it is the same the same of type, but I transform into a Boolean attribute. So I set a BIP attribute to true for all the nodes, and then I assign false to the nodes that are institution. Then I also color the person and institution with light blue for person and orange for institution. I can do more or less the same things with edges. Here is the function to count them. here it is the set of edges. You can see here is a set, a list of couple basically. And I can access a specific edge. For example, I access to the fourth edge. And I can access to the attributes. For example, here I can access to the attribute relation type of the first 10 edges. I don't speak German, so I'm very basic level, so I don't know most of that, but I will do. And I can plot a first version of this network. Okay, while it does, I can explain a bit the code. Here we have, simply plot the graph. I can set vertex size, the layout. Here I use a Flickenmann, which is one of the most used. These algorithms for layout are based on physics with repulsion forces, let's say. There are a lot. I don't have here the time to explain this, but I already choose the one that fit better, let's say. Then I assign a shape according to the type and also the color, as we saw before. So I assign, for example, a square nodes to institution and a circle to the person. And these are, for example, how much the edges are curved, the width of the edges, and what we mentioned. This. So just two. Here we have the network. As you see, it is directed. These very small arrows are maybe easy to see. And we have a large component connected, and then a lot of small components, some of them very, very small. So as I told you on Monday, it is the normal situation. And you can see also that there are some nodes with very high degree that are basically some institution, and then a lot of nodes with degree 1 for the isolated components, but also here you see there are a lot of persons that are connected to only one institution. Okay. No. Okay, then I plot the degree distribution, as I told you last time. Sorry for the very basic plot. It's a bit poor usually, but I think it's okay. So here we have the degree on the x-axis, and on the y-axis we have the probability that nodes have this degree, so basically the portion of nodes with this degree. And here also we saw there are a few nodes with a high degree and a large number of nodes with low degree. So and so I can compute assortativity, and we see it is a number, it is 0.14, that is actually a sign of assortativity. As I told you last time, assortativity goes from -1 to 1, but actually, basically, most of the times from -0.5 to 0.5. So 0.14 is a sign of assortativity. And clusters, you can see here, let's say all the components of the nodes. I wanted just to show you all the output. The output is made of 3 parts: a membership, so a vector that tells us for each node to which component it belongs to. Then a vector that for each component tells us how many nodes there are in, and then the number of components. So this side is a vector with 92 elements, and you can see that the giant component is the third component with 719 nodes. And okay. And then I want to isolate this giant component and work only on it. So I can build the subgraph made by this component. So I use this function induced subgraph, and I tell that it has to take the graph G and all the nodes that satisfy this this condition, that membership is equal to maybe I don't. Okay, I forgot to explain this. And also to run. Here I assign. I create a new attribute membership to for the nodes, and I assign the membership, so the first element of the output of clusters, so that now I can simply know to which component the nodes belongs. And here I selected only the components that belongs to cluster 3, so to the giant components. And I create this network, and I have here a summary. Now I have 719 nodes, and also less edges than before. And you see I inherited all the attributes, so there are no problem. And now I want to assign, for example, a degree attribute to the nodes. So for each node, for example, here I can write for node 4 the degree is GC. Okay, so the degree of node 4, for example, is 2. And I can plot the degree distribution also for this network. We can see that it's quite similar to the previous one, and this is natural because I cutted some nodes here with low degree, so it makes sense that the degree distribution is the same. I can see, for example, which is the maximum value of the degree here and the minimum value of the degree. And if I want to access to the node with the maximum degree, I use this switch max that gives me the index of this node. So just to show you that this, for example, is 226 has degree. Yes, not G. This has degree 130, that is the maximum degree. And yes, I already wrote that. I am consistent with myself. And the label is that this minister at Presidium is the
Makes sense.
It makes sense
Because it's the highest level.
Yes, it's the highest
entity.
connected. I guess the degree node. And so now I create a new attribute that I will use for the visualization. Vic, let's say very important person. I assign this. I assign 0 to all the nodes, and then I assigned one to the nodes with degree more than 40. Why I chose 40? Because if you see here in the degree distribution, you see that more or less if I put a cutoff here, so let's say a line in which I say I take only these values, there are a few values, and I only want to to show in visualization the labels for this VIP for this VIP people, let's say. This node, actually, we are still in a bipartite. So I plot here. I don't use different shape here, just color for distinguish institution and person. And yes, unless it was the same as the other time. Okay, you can see here I have, for example, this is a large, maybe it's not so readable. Okay, but these are the highest degree nodes. I hope that makes sense. Okay, so but we still have a bipartite here. And now what I can do with a bipartite, I can transform into a different network. Actually, it will be, I don't have Blackboard now, but maybe I can use Google. Okay. Yeah, for example, this is perfect. So you know, when I have a bipartite graph, I have nodes of two types connected among them, and I can obtain two projections. So basically, the two projection as the nodes of the two types. So I obtain here, for example, I have user items. I obtain a network for users and one for items, and I put a link every time that two two users are connected to the same item. So, for example, here A and B are connected to one, and so we have here a link. And I put a weight that indicates how many times this happens. So, for example, AB as 3, because as you see, we have AB are connected to 1, but AB are connected to 2, and AB are connected to 3. And so I obtained a weighted network with weight on edges. So this is the function in iGraph to create a bipartite projection. I run it and I obtain a list of two graphs. And I can, okay, I have to specify the types, and here it is the reason for which I created this Boolean vector before, Boolean attribute before, because it works only with a Boolean vector of type. And then I can access to each projection. Simply, for example, here I have the first graph. This is the graph of institution, and you can, as I told you, there is a weight. So I can here do summary. You can see it is nodes made. It is a graph made of 168 nodes and 818 edges. You notice that I inherited all the attributes for nodes, but not the ones for edges, of course. And the only attribute for edges here is weighting. I want to tell you that here, of course, we lose some information because, for example, before we saw that the graph was has multiple edges, and also the edges were typed by the type of relation, so we lose this information. We could also model in some other things, but I wanted to show how I think that to do a good analysis, of course, we'll have sometimes to cut some information, and you know, following the paradigm that less is more. And okay, so for example, here we have the maximum value of weight is 128, just to show you. So it means that two institutions yes, were connected to the same people when 128 times. And I can assign here, I can create a similar attribute as I did before. Here, VIR for very important relation. I assign 0 to all the edges, and then I consider only the edges with weight higher than 30. And I will use this attribute to color the network. Then I have to recompute the degree, because of course there is actually the degree attribute that I computed before, but it is not the same, so I need to update it. And I can again set the VIP attribute to consider the hubs, so the nodes with highest degree. And I can plot here what I used here. This is another, yes, this is another layout, just to show you different. And you see here I plotted the sides. It's not the same for all the network, for all the nodes. I can assign this, for example, that is the size is proportional to the degree of the nodes, and also the width of the edges is proportional to the weight of the edges. And I color here so here, for example, we have the largest weight are enlightened. I don't know if you see in blue, and the other are gray. So choose the better color. But anyway, it is also this higher weight are also highlighted by the width, so it's easy to see. I have you see that I have very clustered portion of the network, so institutions that shared a lot of person affiliated to, and it is quite this is actually quite interesting, this because I expected that this high weighted edges were among high degree nodes, for example, but I wanted to know which is these two nodes connected by an edge with a large weight. So I obtain, this is the ID of the edges with maximum weight. And with this, these commands ends gave me the, if I run just this, if I have an edge with ed max ed, so for example here the edges which is 264, I can obtain the two nodes that are incident to the edges, and so one is 77 and one is 120. And if I want to see the label of these nodes, I simply do this. So the large connection was about this Minister at Presidio, that was the highest degree, and Ministerium of the Class Okay. So I don't know if this makes sense, but it is strange, for example, for me, that this does not appear in any top 10 of degrees or betweenness, for example. So it seems to be something that it's really, let's say, a bit, it is maybe important, but not in a, let's say, for in top 10 for network science. But I didn't check all the measures, so maybe. And okay, so for example, here I can compute the betweenness for all the nodes. As I told you on Monday, the betweenness is the number of shortest paths that pass through that network, so that node, sorry. And here I can highlight the first 10 I values of the nodes. I sort, it means that I sort the vector of the betweenness value in a decreasing way, and then I take only the first 10 values. And now that I have the values of the highest betweenness, I can build the subset of the nodes that have that has these values. And if I show the label, okay, this is the top 10, let's say, of these highest betweenness and centrality nodes, and you know that nodes does not appear, and I can do the same for the hubs, and so here we have the first 10 nodes with highest degree. And then I can, for example, compute the diameter of our network, that is the longest possible shortest path. And you know, this is the longest, meaning that these two are probably the two more distant institutions. Then we can switch to the other projection, the person projection. It is another network. As before, I inherited the vertex attributes and not the edges, but there is a weight. I can do as before the degree, this VIR, VIP. I set another layout. I can set the layout also outside of the plot, and then simply leave with this variable layout. I did several type of visualizations so that you can have some different choices. And I can plot this. And actually, here we can see that it is also more clustered than the institution. And it makes sense because you remember that in the bipartite there were a lot of persons related only to one institution. In particular, there is this very big cluster that's difficult to visualize better, actually. Yeah, I didn't pay many attention to the visualization, sorry, but it is not so important now. You can see here there are also some more higher weighted higher weighted hedges, and so maybe it makes sense to show here the community detection algorithm. So here I can see, for example, the maximum value. It is among these two people. I want some feedback from you. That are maybe, let's say, that share more institutions. It makes sense.
Yes, makes sense.
Okay, and okay, I can again plot the bridges and hubs, and you can see that actually they are not the same. I just wanted to show you, as I told you on Monday, that the different centrality measures define precisely different type of centrality. And so what is important for one, maybe it's not for the other. And indeed, you see here there are no, at least maybe few overlaps. And I can compute here, for example, the clustering coefficient, that is the measure the measure for how much is connected the network, so how many triangles closed, and the assortativity. It is quite clustered. We can also see, and the assortativity tell us this is also assortative. And okay, this is the community detection. So I can simply use this common cluster Louvain that implements the Louvain algorithm. That it is an algorithm that look for in the different partition of the networks, the one that maximize the modularity. And I assign this membership to this attributes community, so that I know for each node to which community it belongs to. I use this palette, that is a palette of 12 colors, since the community are 12. I can show you. And okay, then okay, with this I assign a color direct. So I have the palette is the vector of the colors, and doing like this, so assigning here inside the palette the vector of the membership of the community. I simply can color all the nodes as a community. So all the nodes in the same community have the same color. And here I also write some code, for example, to color all the nodes, all the edges between different communities in gray. And here I will color all the edges from the same community. So I go through all the edges, and if the edges, if among the same community, I color with the color of the community. So it takes maybe a bit. There will be also maybe easier way to do it. Okay, we need to wait a bit. Okay, then when we do that, we could also plot the network. And you see here, I can simply use the color, assign it to the relative to the community. It is done. So I can plot. And this also maybe takes a while. Okay. And here I didn't plot the labels because that's maybe less informative. But here you can see I obtained 12 communities that actually are not exactly, I mean, the number of institutions were much more. So it will be actually interesting to see which communities, let's say, which institution are involved in the same community. And also, one thing that I wanted to do, it was that I couldn't refer this because it was too long. I already finished my time, but in the first network, every edge was labeled with a date. So you can see here in the projection we have this idly connected region of the nodes of the network that actually made the network more unreadable. So we should find a way to remove some redundancy of this network. And actually a way could be considering the date, because each relation type has a starting date and an ending date. So maybe we could do the projection according to the date and create the nodes of the projection only if the two persons were in institution at the same time. I think that with this approach, we could obtain a more significant network. But it was just to show you some possibilities. Of course, there are others, and I mean, I've done, but in 15 minutes, I only wanted to give you an overview of the possibility. Okay, so we have questions.
Thanks very much. It's not a question, but rather a comment. I apologize for the poor quality of the data, because I know exactly where your kind of the stuff that you showed when you were referring to these two ministries. I know exactly why this happened. This is because we obtained the data from these printed volumes, and I didn't cluster them according to the whole government time span for the whole thing, but I clustered it for the volumes that are spanning this this ministry. So can I move it here? No. Sorry. So this is exactly what happens. you mentioned this ministry of, this is like one government.
Yeah.
Yeah. I'm sorry.
You need to stop sharing.
Okay.
It's my mouse
like this,
pointer.
or maybe I have to do.
It's okay. It's okay. You just. Yeah. So, what Marcella found out was that that Schornstein is very important as a.
You're still not sharing. Are you sharing?
Yes, I am.
The other
Aha, shit! I'm sharing the other screen. Damn it! I can't. Yes, but I can't find my mouse pointer in any of these. So I'm sharing, yeah. So, yeah, so there we are. So these ministries are related. So one of these big blue boxes where there's the Schornstein ministry with 7 volumes of data. Basically the ministers are all the same over the whole time span, or most of them anyway. And still we've got 7 volumes of data in there, and I didn't split it, I didn't combine the time spans because I didn't know if there is a change in the personnel during the volumes. And the same is true for the Ministerium Erzherzog-Rainer, which is the one with the 9 volumes. So that's probably why these two were highly connected, because yeah, they had all the same ministries within all, and it's ×9 and ×7 for this thing. So probably to get really results that say something about the actual ministers and not about. Yes, it has. Yes, it has. I can show you one example.
Where are the volumes in the model, in the data?
Yes, I know. And that's exactly what's happening. I'll show you in a second why this is. I mean, this is going into detail, but
I think if it's fast, it's worth it because it demonstrates again the relationship between the sources and your data, how you extract it from the sources, to what you do finally in the network. I remember a talk by Johannes Kaiser Capella where he talked about an ancient Egyptian social network analysis, which resulted in nice graphs before somebody identified that every cluster is represents just one document. So there were all the names. Yeah. Yeah, I don't know the author anyway, but so the classes look very nice, and it was a very nice network, and all analytic methods produced something which showed a new perspective. But the perspective was not new in the sense that the social network was like this, but was only the recording of the social network was like this. So all the people which were mentioned in one document, of course, cluster.
Yes, of course. It was not informative, let's say.
Yeah, completely uninformative. It tells us there are documents. That's fine. Yeah.
No, but in this case, for example, okay, we should maybe look a bit more in it, but the obtained.
But that doesn't. This is only the references. What's in the network is this relation to the right side. It doesn't matter what the reference.
Yeah, but these guys.
We need a connection over the whole one connection over the whole period. It doesn't matter if it's in 5, 10, or 6 volumes.
No, it's in this case it is because the time spans are kind of bound to the volumes. I duplicated the rows according to the number of volumes.
If I remember correctly, when we imported the data,
we tried to match it.
Yeah, we extended the time period to the end of the government, and
So there is here
over the end of the volume.
So here is the one entry,
yes.
52 to 59, which
yes.
covers more than one volume.
Yes.
But just one entry, so it's not for each volume copy of the same.
We did it only for a couple of relations, unfortunately, because you see that the first line and the fourth line, they are immediately, he was Ministerratsvorsitzender up to 13th of March 53, and then on 15th of March he began in the same role again. Because we didn't know, because we were running the same thing over also not over volumes that are not covering the same government. So so you see that the same relation appears here, like in the first, in the fourth, and in the seventh row. It's the same relation.
With different time spans, or they are sequential, and we are losing the sequentiality of the time spans if they're only looking for the relation between office and person. Which would be another interesting approach, because then we have kind of layered or changing in time, so we would have a new dimension. Marcella, talk about this if you like.
Sorry,
I know that you have knowledge about this, about changing networks and
time. Yes, I am interested in doing it. But as I told you before, it's actually interesting also to simplify the final networks.
Yes. Any further questions? Any problems you want to put to Marcella while she's sitting here, still here?
I would have a question, in the sense that I saw in the ministerial council entity database that dates are not standard compliant, in the sense that I saw that they are in a very typical German way and not in the ISO way. So, I mean, are you having a two-step approach, or I'm curious to hear what how you are dealing with this problem, because we have this very same problem too, because we are in Munich. So
we produce the data with the API software, and what we have in APIs is like 4 or 5 different dates. So we have a date that people can enter, the researchers, that is a string basically, and then we have a parser that tries to parse these dates into ISO format. So there is then an ISO format start date, so that we can have flexible dates if it's not an exact date. So you could, for example, enter something like around 1860, and then the time span would be between 1st of January 1860 and end of December 1860. So we have several ISO dates and one written date, and I guess Marcella probably, she's showing
for example, here I tried.
Here. And what you see here in this, when you scroll up a bit, there are these dates. So you can add something where for example, this March 1888 means that there is no exact date in March, but you know it's in March, and then you can put in this brackets the date that you want the system to use for sorting. So you can override what the parser
Actually,
does.
I was about to do something with this, because at the beginning I saw only this and this, so I removed all the null, and they were a consistent number of dates, and then I wanted just to with some regex to let's say extract on the year, just to make a first try. But then actually there was this, and so it was a bit difficult for this.
Yeah, there is another, so there are these other date variables that you could use for sorting and calculating in
I mean,
the graph.
with much more analysis we can also do it.
And apart from that, we imported some of the data from Excel sheets, and Excel screws up the dates if they are before 1900. Don't use if you have to use spreadsheet software for data input, use the NeoOffice or LibreOffice thingy.
But it's normal, that data. I mean, data cleaning is
always data cleaning is definitely something you have to consider, and even taking into account this kind of the approach Matthias said in this double data is a typical approach where you say, okay, I want to keep as close to the source in one field, but I use something which is wrong from the precise historical point of view, but which helps me to do what I want to do. That's a very, very standard approach and highly recommended to do this.
There is a discussion in the chat.
Yeah, please.
I lost the connection between, so.
Okay. Lucas White, do you want to ask her a question, or should I read it?
I can ask the question, but I think my mic's not too good.
That's very low. We hear you very clearly.
Okay, so yes, I mean, it is just actually the graph is the same. You can just maybe because every time the layout is let's say computed, because as I show it here, for example, in this visualization, I compute the layout inside the plotting function, and this means that each time that you plot, you recompute the physics of the repulsion of the nodes, and so it is not exactly the same because there are different possibilities, but the network is of course the same. If you want to fix the layout, you should do like this: put the layout outside the plotting, and then assign to a variable, and then if you use the same, you always have the same visualization.
Would be completely the same because as it is iterative, I would expect that
Sorry?
the method is iterative and starts with arbitrary values. So in theory, it does not have to be completely identical, does it?
No. I mean, it's just I mean, it does not change the structure.
The structure is the same, of course.
Yes,
but it's only the visualization.
Yes,
which
only
looks a bit different.
The pointing, because depend of which point it starts, and it's not. There are some random.
But defining the layout would fix this.
Yes, it fixed the let's say
the starting points.
And also it fix also. You can also fix the singular. The singular position of the node.
So you could even say, okay, I want to have
three-dimensional plots, yes. And also, I wanted, maybe it's not so easy now, but there is also this network is another library that is actually more. I can try to have more interactive. Visualization. If you,
where you can change single positional.
You can also, yes, you can use, for example, in a web page.
This up there somewhere.
Because you open in a browser is better. And here, for example, if you see, if I zoom, I can also move. See, now I did a very poor version, but for example, you can see if I plot on a node, I only see its neighborhood. There are very, very different possibilities with these networks, but the visualization was not my main goal here, so I didn't